So we understand now that the deep neural networks are in a way better than shallow neural networks. And although we don't really understand all the reasons at this moment, probably why that is the case, this is clear. And so the question is then whether other methods would also perform better if we would make them deep. And so, yeah, you can, of course, any method you can imagine, you could also imagine how to make them deep. But I think one thing which is very appealing in a way is to look at Gaussian processes, which are widely used in machine learning, and make them deep, and then study the properties and what depth can help for Gaussian processes. And we will see that in these two talks today. So here's a brief overview about my talk. First, I want to talk a bit about the deep learning, and from there, I basically want to motivate again the use of deep Gaussian process priors. So here, my main message will be essentially that deep learning is already something which is close to Bayesian in a way. And then in the second part, I want to talk a bit about how to compare the deep Gaussian process regression and neural networks, deep neural networks. And then finally, the third part will be the consistency and the contraction rates part, where we show then certain contraction rates for deep Gaussian process priors. Okay, so let's start with the first part, and let's start with the deep learning as a starting point. So here's my standard slide about what a deep neural network is. You all have seen that, of course. So you can either represent it as a graph, but we like to really view it in mathematics as functions of this form, where we alternate between the matrix vector multiplication and then component-wise application of this activation function. And the activation function sigma here, the state of the art is, of course, to use the rectified linear unit activation function, which just keeps essentially the non-negative entries of the vectors and projects everything else to 0. And in this formulation, so the L is the depth, and it says essentially how often we alternate between matrix vector multiplication and this application of the activation function. And by definition, a deep network is something which has more than one of these hidden layers. So L is larger than 1. But of course, nowadays, if we talk about deep neural networks, then we really talk about something in the range of 20s to 100, or even a larger number of hidden layers. And the big thing is then, so the free parameters in these neural networks are all the entries of these matrices, and that in practice is in the range of several millions or hundreds of millions, actually, in some applications. And the thing is then to fit these functions to data, and to assign all these, to estimate somehow the parameters here from the data. And so how do we do that actually? So how do we fit the neural network to the data? Well, so if you read this in machine learning language, then it's all a bit obscure. So they talk about coarse entropy and so on. But if you really look into what it is, then what you do is essentially you try a maximum likelihood. Yeah? So ideally, if you could, you would like to estimate, take the maximum likelihood estimator here over this function class that is generated by neural networks with a given architecture, say a given depth and a given width vector for all the matrices in the neural network. And but the problem, of course, we all know this is a non-convex problem. So we cannot find this global minimum of the log likelihood, of the negative log likelihood. So what we do instead is we use a gradient descent method, typically stochastic gradient descent, and then that will end up somehow in a local minimum. But ideally, somehow we would like to do here maximum likelihoods in a way. Okay, so we do that, and so a very crucial ingredient is that we need to initialize this gradient descent method. Okay, and so here for the initialization, it is known that it really matters in terms of how the fits later perform, how well they can predict on new test data. And so what is the standard scheme? Well, what you could do in principle, you could assign all the values to 0. That would be a terrible idea, because then somehow you have all these symmetries and you cannot get rid of them with the gradient descent. So you have to do something more clever. And the standard way is to draw all these parameters in the neural network. Yeah? So we take this neural network class, we have these matrix entries, and all these matrix entries, we draw them independently from a distribution, either typically a normal distribution or uniform distribution, and centered, and the variances are assigned in such a way that these matrices here, they're basically random orthogonal matrices. Yeah? So that we do somehow a random walk but if we go to the different, if we look at this in a successive way. So that's the way to do it, and that somehow is known to perform reasonably well, and that is the default if you go on TensorFlow and you use for instance Adam or so. Okay, so what we just want to make sure here is that the initialization is like a sort of a prior here, and it really influences how well the whole thing performs in the end. Okay, so here, what do you get actually? So we put the initialization, we put that on the parameters, but in the end, we are interested, of course, in these functions that we generate, right? We have these two perspectives. Either we can look at this function in terms of all the parameters, that means all the values of these matrices, or we can look at the functions that we generate with these parameter values. Okay, so there's two perspectives, and if we initialize, we put that on the parameters, the random variables, the initializations, but in the end, we are interested essentially what type of functions do we generate here. And so what is interesting is to see that if we have a shallow neural network, which just has one hidden layer, then it's not so hard to see that under very broad assumptions that these functions that you generate are like stochastic processes, and that will be a Gaussian process, which is centered. And the only question is then what is the covariance structure of this Gaussian process that we generate by the random initialization. And the covariance structure is given by this formula. So it involves essentially here the activation function and also the distribution of the inner weights in the shallow network. Yeah, so they're all drawn IIDs. Yes, that's just important, like what one of these it is a row vector, and one of these weight matrices, what the distribution of that is. Okay, so now you can wonder, for instance, what type of Gaussian processes do we get out of that? And so if you easy exercise, if you go to one dimension and so and say, what you see then is that you get essentially, based on this initialization scheme, you get a very, very simple Gaussian process, which just multiplies your x with the Gaussian random variable, which has the variance that somehow depends on the weight distribution. Yeah, so you don't really get very complex objects here like a Brownian motion, or so a very simple Gaussian process. But what we learn here is essentially that this random initialization, we can see it as a prior, and what it generates in terms of in the function space, it generates the Gaussian process. Now this is a shallow neural network which just has one hidden layer. The question is, of course, what happens if we compose layers, if we now look at the deep neural network and we also randomly initialize all these weights IID. What happens then? So what is the limit of that? So we would think maybe there is something more complex than a Gaussian process. The question is that true? And the answer, well, it depends a bit. So it really depends on how we take this limit. So in a shallow neural network, there's essentially one limit that we can take. We can take this hidden layer, the number of neurons in the hidden layer, we can take that to infinity. And that's the wide limit, and then we get the Gaussian process. If we have several hidden layers, we can take all these number of neurons or units in the hidden layers, we can take them at different speeds to infinity, and then we can get different types of limits. out of that. And well, the simplest thing to consider here is if we take all the hidden layers, the neurons, the number of neurons in the hidden layers, we take them all simultaneously to infinity with the same growth rate. And in this case, it is known that even although we have this composition structure in the Gaussian deep neural network, the functions that we generate with this random initialization are still Gaussian processes. Yeah, so we are still in the space of Gaussian processes. The only thing that differs now is basically that the covariance structure is more complex. And so how is it? What is essentially one cannot give the explicit formula for the covariance structure, but you can write it down as in a recursive formula. So, and then try to understand it a bit. And the way to prove that is, for instance, by using central limit theorem for exchangeable sequences, and that has been done in for instance, this paper, and that's well known. Okay, but as I mentioned, we also can take other limits. For instance, what we could do here, let's explain on this slide. What we could do is we could take, say, a deep neural network with 3 hidden layers. So it has and 2 hidden layers. We let 2 hidden layers tend to infinity. And the third, the middle hidden layer, that one we keep, say it's just 2. We keep it fixed at 2. Yeah. Now what you see essentially, now you can think about this as a shallow neural network composed with a shallow neural network. And so we know that this thing here, this one, this converges to a Gaussian process. And this one here, the second part, also converges to a Gaussian process. And in the middle, nothing happens because we don't take a limit. So what we get out of this is from this random initialization, it will generate a composition of two Gaussian processes. Yeah? So it will be something Gaussian process composed with a Gaussian process. And that's not a Gaussian process anymore, so it has a more complex structure. And so what you can see here is that, for instance, also with certain architectures, and so in principle, which are good initialization scheme, you can also get more complex objects from the initialization, such as compositions of Gaussian processes. Okay, so that's a bit my summary here. So as you know, I wanted to motivate that by saying deep learning in the way it's performed is already something close to Bayes. And so first of all, it's a likelihood-based method. So we try to do maximize the likelihood. And secondly, it really depends on the initialization of the stochastic gradient descent, and that really acts like a sort of prior information. So the stochastic gradient descent cannot move anywhere afterwards. And the way we initialize it, essentially what we do is if we look into that in function space, then these initialization schemes, they generate either Gaussian processes or deep Gaussian processes, which means composition of Gaussian processes. Yeah. Okay, so that's a bit the Bayesian view maybe on deep learning. And so what we could now look at is to non-parametric Bayes. And of course, you all know this is a non-parametric Bayes audience. And before I come to the question that was asked, just let me finish I will finish the slide. So yeah, if you notice, of course, it's also Bayes is also likelihood based method. And secondly, we know that for non-parametric problems, also the choice of the priors is really important, that some priors they work and other priors they don't work. So it's a bit the same story here as what we observe in the deep learning. Okay, so there's a question that I will read out as well. So we also have a prior on the choice of activation function value versus other activation functions. And does convergence depend on the form of the activation function? Okay, so let's go back. Yeah, very good question. Thank you, Jennifer, for this question. Here, what we see essentially is the activation function is if it has some sort of regularity, it doesn't really matter. We'll always go here in this case to a Gaussian process. Where it matters is in the covariance structure. So if here, for instance, we have value, and then we get this process, but if you take another process, you would get a different covariance structure. But otherwise, unless it's extremely irregular, it doesn't matter in the, it will still be a Gaussian process limit. Yeah. And so, of course, can we take a prior now also on the activation functions? I'm not so sure. So that would be something very different from what people do. And it's also not clear how to train such a neural network then in this case. Okay, so let's go back here. So one thing we could do as a sort of intermediate step, right? We could look at what is called a Bayesian, also another thing what is called a Bayesian neural network, where we just take essentially these functions that are generated by neural networks, when we take the same initializations as people do in deep learning, and that means, but the initialization is now considered to be the prior, right? So that would be a very natural extension and for Bayesians to do that. And that has been done. I mean, it goes all the way back to this book by Neil in 1996. And so where people have studied that, putting priors on parameters and then studying the posterior distribution. And then basically we would have, under these conditions, we would just have another way to generate Gaussian priors, more or less, because in the right limit they are Gaussian. We have seen that. And we could study the posterior for that. That would be one possibility. It would be different though than if like the classical Gaussian process regression and non-parametric base, because we have a different parameterization of the Gaussian process with these functions here, and so that also affects, of course, what the posterior is in the end. But so we have decided not to do that, not to study that directly, and other people have done that. For instance, great work by Veronika Rokova, and so where they study posterior contraction rates for this object. Or we rather thought we want to go one step further and avoid all this structure from these neural networks, and we want directly go to deep Gaussian process priors, because we think that might be really something for, yeah, that has maybe even better properties than doing deep learning, and although it's maybe computational much harder. And so therefore what we decide is then, okay, let's go one step further away from the deep learning and really go and study deep Gaussian process priors. Okay, so let's now move to the deep Gaussian processes. So there's different ways to say what a deep Gaussian process is. Some people think about it like in terms of conditioning in a hierarchical way. And here I interpret deep Gaussian processes as compositions of Gaussian processes. And so just to see that this generates interesting objects, I think we can look at iterated Brownian motion, which is a well-studied object. And in probability theory, we just take two Brownian motions, either, I mean, independent or the same one or so, and then look at the composition of these two Brownian motions. And what is known here is that this is not a Gaussian process again, and also the smoothness properties of the smoothness property of this process change. So you know probably that the Brownian motion has smoothness almost a half, filter smoothness almost a half. And so if you compose two Brownian motions, what happens then is that the smoothness index decreases to a quarter. So it's a half times a half. So it's almost a quarter. So here you see that compositions, they can deteriorate the smoothness, for instance, quite a bit from a half to 1/4. And you see that also very nicely in this simulation. So on the right, we have this iterated Brownian motion that has much rougher paths than the Brownian motions. Okay, good. So let's go now to the last part of the talk, and now I want to talk about the convergence analysis that we did for these deep Gaussian processes, and that the main part is really the construction of the good deep Gaussian process prior. And before I come to the construction, I want to talk already about the statistical estimation problem that we would like to address with these deep Gaussian processes. Sure, and here what we want to do is we want to essentially do a non-parametric regression in d dimensions, a multivariate non-parametric regression. And in this case, we observe these pairs xi, yi's, and there's this unknown function f that connects xi's and yi's, and we want to recover this function f from the data. And so this is one of probably most studied non-parametric models, and we know that there are many methods that perform very well for this estimation task, and they achieve minimax rates and so on. And so we don't need deep methods for that. In order that we really need deep methods, we need to put somehow structure on this regression function first. So we cannot just assume it's smooth, or it's we need something more structured in order that it really makes also sense to come with a deep method. And so how do we put structure on this regression function f? Well, what we assume here essentially is that that this function f, it can be decomposed into smaller bits. Yeah, so for instance, here's an example where you could assume, for instance, that the function f, so it has 5 variables, that it consists of 3 inner functions, g1, g2, g3. Each of these functions only depend at most on 3 of these 5 variables. And then there's an outer function h, and that is a function of the 3 outputs, g1, g2, and g3. Yeah, so it's a more structured approach. And here, I think it's really useful to think about these structures as graphs. And so the graph representation of that would be then this graph here. And what really matters is the in degree of these nodes, because that says essentially like how many variables these functions depend on, and that's then how hard it is to estimate this function from data, or recover this function from data. And so there's probably, you noticed there's a lot about now estimation of or recovery of algorithms or so on. You can see it a bit like these compositions, right? So in algorithms we have a lot of like little parts, and they get combined into larger things. And so that gets, in the end, if you would really write it down, would get these sorts of composition structures. Many other things, how to motivate it. Also a lot of structural constraints that we have explored in non-parametric statistics, such as generalized additive models. So they all have this form in a very specific way. So it generalizes, in this sense, many of these structural constraints that we have seen or studied before in non-parametric statistics. Okay, so here's my function assumption, the assumption on the underlying function that we want to learn from the data. So that's in a way has nothing to do with the deep Gaussian process. It's just a way we model the data, right? So it's a non-parametric regression model, and we put this assumption on the regression function f. So what is this assumption? Now it's a bit a technical slide. I have to. I'm sorry for that. So we assume that this function f consists of a composition of q plus 1 functions. So that's a misleading notation with here. So here would be q equals 2, 1. So sorry, it has the g0 and the g1. So don't confuse that with the h. That was a bit unfortunate, I think, here. And so these functions gi, they are functions from rdi to rdi plus 1. So just say from the real from some dimension to some other dimensions. So it doesn't really matter what these GIs are. What is important is that we assume that these GIs, they only depend, all of these components of the GI only depend on TI variables, and TI is at most TI, of course, but we assume it's smaller. So in this example here, we have the DI, the D0 would be 5, because that is depends on 5 variables, but T0, that is only 3, because each of these component functions only depends on at most 3 variables. Yeah, so the in degree of these 3 guys is at most 3. Okay, so we have these TIs, and then what we also have to define what we call the effective smoothness. So it's beta I star, and that relates back to essentially what we also have seen already with the composition of Gaussian processes. So if you compose functions, then the smoothness can go down. And what we need is for, of course, non-parametric regression. It's really much the convergence rates. They come because we separate the regression function from the noise, and they have different smoothness properties and so on. But what we really need is, if we put smoothness on the GIs, what is the smoothness that is induced on the function f here? Yeah, so that is the question. And if you study that, so then if we put a smoothness beta I on the function GI, then this induces essentially that the function f has a smoothness beta I star, and there's this additional factor here, which is always smaller than 1. So it shows how much the smoothness can deteriorate by composing functions. That is essentially what happens here. Okay, and then so in earlier work, we have proved that for this function class, the optimal convergence rate in the minimax sense is of this form. So you get essentially to see this typically enter the -2 beta over 2 beta plus d rate in non-parametrics. But now the betas, they're replaced by beta I stars, these effective smoothness indices, and the di's, so the dimensions, they are ti's, and ti, I already mentioned, that can be much smaller than the di, so we don't necessarily suffer from the curse of dimensionality. And then we take essentially over all these q plus 1 functions, we take the worst rate, and that determines what the minimax rate is. And so we have shown before that sparse neural networks, sparsely connected deep neural networks, they can achieve this convergence rate. So it is achievable by at least one deep method. And the question is now, okay, so we set it up in this way. The question is now whether deep Gaussian processes can achieve this convergence rate as well. Okay, so now let's come to the construction of the deep Gaussian process prior. So first of all, we have to put a prior on these composition graphs. On composition graphs. And once we have put the prior on the composition graph, we essentially put a prior, a Gaussian prior on each of the edges. Yeah, so again, let me go back here. So we have the graph, which is just like how our function is decomposed. We look at different graphs, we put a prior on different graphs. And once we have picked a graph, we put on each of these edges here, on each of such an edge, we put a Gaussian process, and that generates our deep Gaussian process prior. Okay, so how do we start? Of course, there's always this model selection problem. So if you put a prior on a large graph, you can better explain the data. So you have somehow to penalize the large graph, and that is quite standard. So there's techniques how to do that in a way to put the right mass on every graph. And so we follow basically this sort of approach from the model selection literature on how to put a prior on these graphs. Now the second part is once we have put the prior on the graph, we have to put these Gaussian processes on the edges, and there are now some problems here. So if we put Gaussian processes on these edges, what can happen is that if you compose two Gaussian processes, that you get a really wild behavior of this composition, and with a certain probability, a small probability, that can happen. But for Bayes, for non-parametric Bayes, also events with small probability can somehow they matter for the posterior distribution. So we know that it's a small ball probabilities, and so they are enough. And if you have somewhere small probabilities, then you see that in the posterior. So we also have to take care of this very wide behavior that can happen. And so, for instance, it could happen that the first Gaussian process, it generates a large path, and then so the next one lives on a very large domain. If it again generates a large path, then the whole thing explodes. It generates huge or huge variability in the function. So it becomes much rougher. And then say the average path that it's very hard to make that precise, but in a way like how you see it on later in a plot, so that is like what typically happens, and then there's some really extreme paths that happen with small probability. And so we had somehow to regularize this path behavior that can occur due to the compositions. And what we did, well, what people in practice sometimes do with deep Gaussian processes is that they put a link function, a bit like an activation function, in between that smoothes out, so it transforms everything again between -1, 1, or so. That can happen. That is a proposal in the literature. What we did here is we only look at sample paths that are such that the path is always between -1 and 1. Yeah, we condition on these paths in the construction. And then there's a second condition that I also don't really like is that we also have to condition the path to be close to, in a way, to a Hilbert function. Okay, so it's also cannot only like the composite that the function values get large, but also the variation can get very large at some point. And that can also lead to similar effects. So we also condition that on to have that they are close to Hilbert functions, and we can show that happens for, I mean, under certain conditions that happens with positive probability, such that if you draw from this process, you find enough paths that satisfy these constraints. Okay, so then we tried for a long time to avoid this conditioning. We thought that should be avoidable. That's not nice, and so, but in the end we gave a bit up, and we because also again we made this analogy with the deep learning, and there you see very clearly that also there you have to take care of compositions, and that compositions due to stacking layers on top of each other can be very bad, and this because I mean deep learning people really think in terms of the algorithm, not so much in terms of the functions that you generate, but they realize that you can get these exploding or gradients, or the gradient goes to 0 and so on, then it doesn't move anymore, the gradient descent, and so they have found ways to stabilize the whole network such that that you don't experience that during the training. And that's one of the strategies is batch normalization, probably the most well-known one. And so it has a bit like the same effect as what we do, but it's of course you can do it on the samples. And as a Bayesian, if you're full Bayesian, you have to first select the path, and you cannot look at the data, so you have to do that based on the just the functions that you generate with your prior. So it's a bit a different thing that we do, and therefore also it looks different than batch normalization, but it has a similar flavor, at least our approach, which is conditioning. Although I don't claim that it's all done. I think it can really be improved also theoretically still. Okay, so that's a bit my my claim here is that the conditioning in some sense it's necessary, but maybe not in the sense as we have it. And there are many reasons how one can argue, for instance, by the deep learning, but there's also something, maybe you know the Kolmogorov-Arnold representation theorem that says essentially by composing two functions, you can represent every function exactly. So if you just have one function, since you can't, like typical approximation schemes, it cannot work. But if you compose, you get so much richer function classes, and it completely behaves in a different way after composition. So there is really something. And the question is, does it help for the Bayesian analysis, or is it rather bad? And we have to exclude it. That's not so clear. And in our case, for our analysis, we decided in the end to exclude it. Okay, so now I'm almost at the end of my talk. Here's the main theorem for this prior construction of this hierarchical prior construction of a deep Gaussian process prior. We can show that the posterior contracts with this optimal convergence rate, which we have seen before and shown before for deep neural networks as well, but it also holds for the deep Gaussian process prior. And in the second talk that now follows by Matteo, he will show that a simple Gaussian process, which is not deep, that cannot achieve this rate, and that there's really a polynomial gap between that and this optimal rate. So I don't want to talk much more about this here. I think that is really the second talk, the very recent work that we finished recently. Maybe just as the very final things there, bit on the proof. So how did we prove this result? Interestingly, maybe this is the whole message. You don't need to read all these formula. What is interesting is that you can essentially build on this very, very nice theory by Art van der Waard and Harry van Zanten on how to prove posterior contraction rates for Gaussian process prior. So they show that all depends on this one function, which is called the concentration function, which combines the approximation part in the reproducing kernel Hilbert space associated to the Gaussian process and the small ball probability part associated to the Gaussian process. And you can extend that analysis essentially to the deep Gaussian processes. But it's not just a straightforward extension. You also have to include a bit more. And one thing we have to include is this additional parameter alpha. So before, essentially in this paper by Art and Harry, everything was for alpha equals 1, and you had to check this condition only for alpha equals 1. And now, because we have the compositions, one has to check this inequality for the concentration function for all alphas between 0 and 1. And what comes out of this inequality, if you can typically verify it for the standard example for Gaussian processes, what comes out here is that we get a rate epsilon n alpha. Now that depends on alpha, and that goes into the rate and as a factor, so it becomes beta times alpha instead of just the beta. And that also explains everything with these effective smoothness indices. We always have another factor there in the rates, and that comes essentially through this argument here. That's really the workhorse of our proof. Okay, now my time is up. Just to summarize a bit, we started with looking at deep neural networks and argued a bit they have a Bayesian flavor. Then we said, okay, let's look directly at deep Gaussian processes as priors. And then based on the specific problem with the structured regression functions, we built a structured deep Gaussian process, which also looks at compositions, and then puts on each of these compositions, puts a deep Gaussian process. We saw the issues with this conditioning, and that's really also partially still an open question. I think many things can be done. In particular, I think that it would be really, really nice to have some implementations of that. I think these deep Gaussian processes are really promising in terms of mathematical properties, even better than deep neural networks. But of course, it's computationally more challenging. And here, with that, I want to finish my talk. Thank you for your attention. And I think I don't know, Jim is the boss, but maybe we can go directly to Matteo's talk and then take all the questions at the end. Is that fine?
Yeah, let's do that. Let's have everything at the end. Okay, Matteo, you want to?
Yeah, I'll share my slide. Okay. Okay, excellent. Yeah. So thanks, Johannes, and thanks, Jim, for the kind introduction before. So what I wanted to present today is some related work on lower bounds on the performance of Gaussian process regression when we try to estimate the compositional functions, which is some very recent work we've done jointly with Johannes and also Colin and Ray. As we've seen, the hierarchical methods, so methods based on a multi-layer architecture such as deep neural network and deep Gaussian processes, are at the heart of machine learning and provide some state-of-the-art performance in numerous tasks. Results that Johannes presented in the first part of the talk show that these hierarchical architectures can adapt to some underlying compositional structure in the signal, achieving fast, near optimal convergence rates. And when the compositional structure has some low dimensionality, the rates can be dimension free. Another interesting point is that instead, if we look at a more traditional estimation method, in particular wavelet estimator, then Johannes showed that these are unable to adapt to the underlying compositional structure, and instead are limited to some polynomially suboptimal convergence rate, and thus are outperformed by deep learning techniques. Regarding the Bayesian literature, understanding the role of the depth is still in its infancy, and in our work we were interested in trying to advance our understanding by investigating whether non-deep Bayesian method also suffer from some gap in the performance when trying to estimate these compositional structures. And given Johannes' work on deep Gaussian processes, a good starting point for us was to compare the performance of deep Gaussian processes to standard GP priors, which motivated our project. We formulated the result in a multivariate white noise model, which is closely related to the multivariate regression problem introduced by Johannes. So here the goal is to estimate the function f defined on the d-dimensional unit Q from observing the solution y with law PF of a stochastic differential equation when on the right-hand side we have f plus Brownian motion scaled by 1 over square root n. In standard GP regression, we model f by a centered Gaussian prior pi on L2, which we allow to have a general covariance kernel. By conjugacy, then we know that in this model the posterior is also Gaussian, and it has some explicit formulation which we exploit in the proof. We then evaluate the performance of the method by studying the speed at which, assuming that there is some true F0 generating the data, the posterior concentrates around the truth as n tends to infinity. Now, since we are interested in formulating a lower bound, we are in particular interested in a notion of uniform convergence rate, which we define as being sequences epsilon n tending to 0, such that the supremum over some functional class of interest, which for us will be a compositional class of the expected posterior probability assigned to functions f with L2 distance from the true F0 being at least epsilon n converging to 0. So while this is not perhaps the standard formulation of posterior contraction rates, the now very extensive literature on deriving upper bound for posterior contraction rates, including for Gaussian process priors, usually implies this form of uniformity where the function class is typically a ball in some smoothness classes, since the constant in the proof appear to usually depend on norms of F0. Regarding lower bounds for the contraction rates, I wanted to mention the result by Ismael Castillo in classical function space. We lower bounds on the concentration function, which Johannes mentioned earlier, and also a recent work by Agapio and Wang over spatially inhomogeneous base of classes, which exploits some the linear minimax theory over these spatially inhomogeneous function spaces developed by Donoghue and Johnston and co-authors in the 90s. Interestingly, recently a line of work has emerged by Suzuki and co-authors, where they show that deep learning is optimal in these for this spatially inhomogeneous set. Instead, for us, the interest was mainly in compositional classes, which ultimately required some the development of some of new tools. In particular, to derive some lower bounds, we focused on a particular functional class, assuming that the true function F0 is the result of a 3-layer composition, where in the first layer we apply to each component of the variable xp a univariate function F0p. And then in the second layer, we sum over all the functions F0p. And then in the third layer, we apply to the sum a function h. We assume that each function F0p and the function h are Lipschitz continuous, and that the sup norm of each function and the Lipschitz constant are all bounded by 1. Under this assumption, we call script G the collection of all functions of this form obeying these bounds, which are and functions of this form are typically called generalized additive models, and are one of the most common example of compositional structures in literature. The result by Johannes show that for this compositional class, which is a special case of the general compositional framework introduced before. The minimax rate Rn are of the order n to the minus 1/3. So in particular, they correspond to the minimax rate of estimation for a univariate Lipschitz function, showing that thanks to this hierarchical structure, we can overcome the curse of dimensionality by recovering the rate for a one-dimensional function. Also, the theorem presented at the end of the previous talk shows that by suitably constructing deep Gaussian processes, we are able to obtain the minimax convergence rate up to log factors uniformly over the class G. Now, instead, our main theorem shows that this is not the case for a standard non-deep Gaussian process prior. We formulated the result in the following way, showing that uniformly over the composition class G, the expected posterior probability assigned to functions f with L2 distance from the true f0 in the compositional class being at least a constant time a power of n with exponent 2 plus d divided by 4 plus 4d is bounded below by a quantity which is bounded away from 0 and is arbitrarily close to 1/4. So in particular, this will never converge to 0, even if even as n increases. So in particular, then we deduce from this a lower bound for uniform posterior contraction rates over the class G, which necessarily have to be at least equal to constant time the power of n found in the statement of the theorem. And if we now compare the lower bounds that we obtained here to the minimax rate n to the minus 1/3 obtained by deep Gaussian process, we see that as soon as the dimension is greater than 3, then the exponent 2 plus d over 4 plus 4d is smaller than 1/3, so that the lower bound that we obtain here is greater than the minimax rate n to the minus 1/3 attained by deep Gaussian processes, showing that effectively there is a gap which is polynomial in the sample size n of the performance from standard Gaussian prior to deep Gaussian process priors. This polynomial gap, in fact, gets wider as d increases. As if we think that d is very large, then the lower bound that we obtain in the theorem will be increasingly close to n to the minus 1/4, as opposed to n to the minus 1/3, which is the minimax rate. Okay, so I wanted to give a brief outline of the proof, which also reveals some possibility to refine these results. And in the proof, the starting point for us was to show that the lower bound on the contraction rates are in fact implied by lower bounds on the posterior mean for the L2 risk of the posterior mean. And this comes really from the conjugacy of the model. Since then, the posterior is Gaussian and therefore concentrates around its posterior mean. And then we can make this argument precise using a suitable concentration inequality. Then the main challenge and also the main contribution of our work is to provide a lower bound for the supremum risk of the posterior mean over the compositional class G, which holds for a arbitrarily chosen Gaussian process prior. And to attack this problem, the idea that we have is to exploit the Caron-Love expansion of the prior by representing the posterior mean as a series estimator in the Caron-Love basis. And then by exploiting this representation and some explicit computation, we are able to lower bound the expected squared L2 risk for fixed F0 by some quantity that will depend on the coefficients of the expansion of F0 with respect to the Karhunen-Loève basis. So in particular, what we obtain is that choosing an arbitrary finite collection of functions f1 through fn, then the maximal squared L2 risk over this finite collection is lower bounded by a quantity was, well, a specific form is not so important here, but that importantly highlights the coefficients of the expansion of each function fj with respect to the Karhunen-Loève basis. So that in this way we are able to deal with arbitrary GP by looking at their associated expansions. Then the main technical step is to construct a family of finite number of functions which we can control, for which we can control the coefficients in the expansion independently of the basis phi k. And we do this by constructing some localized functions by picking the number of function m as a power of the sample size n, by constructing a grid of point I equally spaced in the hypercube. And then for each point in the grid, we construct around this point a generalized additive function fz by shifting the L1 distance from the variable x to the point in the grid z by a certain power of m, and then by taking the positive part of the result. This can be written by exactly in the form of a generalized additive model, and then we can derive bounds on the Lipschitz norm and the sup norm, showing that each of these functions fz will belong to the compositional class G. And if we think of the plot of each of these functions, what essentially we construct are pyramidal bands centered around each point z in the grid of a certain height, which are supported on very small hypercubes. The characteristic of these functions that allows us to obtain an independent control of the coefficients in the expansions with respect to the Karhunen-Loève basis is that first of all, since each is supported on a separate hypercube, all these functions have disjoint support. So in particular, they are orthogonal in N2. And also we can obtain a precise control of the L2 norm of each of these functions. And then by combining these two properties, we are indeed able to obtain a lower bound for the maximal risk over this class of this family of pyramidal bands, which is independent on the Karhunen-Loève basis, and recovers exactly the lower bound in the general theorem that we derived. Okay, and just as a quick observation to conclude is that the necessity of deriving a bound which works independently of the Karhunen-Loève basis, which we did via these localized functions, means that it's conceivable that if we instead fix a particular covariance kernel in the tire, so a particular Karhunen-Loève basis, the bound that we obtain here could be potentially crude and can instead be refined. This is what we've shown by looking at a specific choice of the Karhunen-Loève basis, which are Gaussian wavelet series prior, for which Johannes has derived a very refined approximation theoretic results that allows us a better control of the coefficients in the expansions. And for this specific class of Gaussian series prior, then we showed that the lower bound on the contraction rates can actually be improved to n to the -1 over 2 plus d, which is now the minimax rate of estimation for Lipschitz d-dimensional functions. If we compare this refined result to the general, we see that since the exponent is always smaller, then the rates that we find in the latter term is always slower than the lower bound in the general theorem, and therefore provides a stronger lower bound for Gaussian wavelet series prior. In fact, this latter rate is seen to deteriorate when d increases, since d is only at the denominator, and shows that Gaussian process regression with Gaussian wavelet prior suffers from a form of curse of the dimensionality. Now, this possibly suggests that the same slower rates affects Gaussian priors of arbitrary form, although extensions to general GP appear to be very challenging due to the need of a specific approximation theory, which instead is available for Gaussian for wavelets. However, our results still shows that there is a performance gap, which is polynomial in sample size, for the recovery of compositional structure between standard Gaussian priors and deep Gaussian process prior, which would then provides a first insight on potential advantages of using hierarchical architectures within the Bayesian framework, which was our main interest for the project. So I think, yeah, I said within the time. So this is just the reference for our work, and thank you very much for listening to my talk.
Thank you. So it was a very good set of talks. Okay, so do you have any questions for Johannes and Matteo? So you can either kind of unmute yourself or put your hand up or type something in the chat.
Yes, hello. This is Shripto Banerjee from UCLA. Thank you very much. I enjoyed the talks very much. I suppose my question can be addressed to either of the two speakers, but perhaps Johannes, because he explicitly mentioned the construction of the deep GP. Can you comment on the smoothness properties of the realizations of a deep GP based upon the construction that you showed, using these different classes of activation functions or otherwise? So for example, the continuity properties of the covariance kernel that emerges from these deep layers and its implications perhaps for interpolation or prediction. Thank you.
Yeah, maybe I can answer the question. Thank you for the question. So what we do is maybe I didn't want it to go into too much detail here. So in principle, you could put say a bound in motion also, or a bounding sheet in the multivariate case on each of these edges, and then you would essentially have a half smoothness a half on all these functions, and that would not necessarily match with the smoothness that you have in the composition. And then it is always the thing in non-parametric base that if the smoothness indices don't match, then you get worse rates, so you cannot really achieve the minimax rates in these cases. So what we do essentially is we also put a hyper prior on the smoothness. We assume the smoothness always in all the layers and all the functions that occur lies between two values, beta minus and beta plus, which are bounded away from 0 and from infinity. And so in this range, we are then adaptive by also somehow mixing over processes, Gaussian processes with different smoothness. In principle, that could, in the Bayesian non-parametrics literature, we know that it could also be taken care of by putting, for instance, a gamma hyperprior on the speed at which a Brownian motion runs. That was work by Arthur, so then they could show based on that they can achieve adaptivity or adaptation. the smoothness, but that is something we haven't explored yet here. So we really put different smoothness indices essentially on each of these edges, and therefore achieved then also the adaptation to the smoothness, which we didn't have in the case of deep neural networks. There, for this result, it was really, we need to know the smoothness indices of these beta i's that occur. But for the Bayesian approach, we can adapt to the smoothness indices. So in this sense, it's even a more general result. Yeah.
Thank you very much.
Mm-hmm.
Okay, so Bonin, do you have a question?
Yes, I have a question to you, Matteo. Very nice talk. So I just want to quickly ask, so is that possible to run some simulation studies to observe the difference of the lower bounds by using GP and deep GP?
Well, for deep GPs, I guess, so this goes back to questions of Johannes log about the implementation of that. I think, yeah, I mean, in principle, like Gaussian process regression is not difficult to implement in the setting. And then perhaps one should then think about implementing deep GPs, or one could compare the performance to perhaps a deep neural network, since it achieves the same faster rate. It is something that though we didn't consider for our work.
I see. Yeah. Thanks.
Yeah. Thanks.
Okay, so there are other questions?
Yeah, I just wanted to ask. So, well, Johannes and Matteo, well, very nice talk, really enjoyed. My question is for Johannes. So the rate theorem that you presented, so if I understand correctly, you are assuming the structural form of this function, like which layer, which variables get involved in that composition, right?
We put a prior on that as well. So we put first a prior on these composition structures, like a hyperprior, which basically you can also see it as a model selection problem. And then conditionally, like a hierarchical construction of the prior, conditionally on picking a composition graph, we then put a Gaussian, deep Gaussian process on this graph. So which also means we also mix over different composition structures. So we don't have to assume we know the Q. The Q was the number of compositions that occur. Neither do we need to know the TIs or so. That is all because we also put a prior. That makes it, of course, also very challenging to implement it in the end. And from the theory side, you can just put a prior on it as well and then adapt.
Okay, that's very nice to know. So at every component, every layer, every piece, you have to do this kind of variable selection, right?
Mm-hmm.
And so, and I guess you're assuming that you have a fixed number of predictors, right?
Yes. Yeah. Mm-hmm.
Okay, but then there's in between layers, the intermediate ones, one can potentially have a much larger number of arguments in the intermediate layers, right? Than the original, because there's so much of you can compose, right?
Mm-hmm.
And so this will, it will have to be basically over all these possible selections.
Yeah, one can show that one only has to look at the Ds, like the what you say in the intermediate layers in these composition graphs, how many variables you can have. I think one can restrict to the Ds to be not larger than log n or so, because otherwise one can already show that so one can somehow do something, but it will grow also with the sample size, the size of the composition graphs that one has to consider. And of course, the large ones get very small weight. So it's one has to sample essentially from all of them probably, but they get very little weight. And in a way, also I think, and that's something we haven't encountered or like worked out in all detail, but many of these composition graphs, they're a bit redundant. So they don't lead to faster convergence rates. And in principle, one could look at equivalence classes and all the ones that lead essentially to the same convergence rate and put them together, and then just have to put prior weight on one of the elements of these equivalence classes, not on all of them individually. But it's very hard to write that down, what these equivalence classes are. So we haven't really explored that. But that might be something which really significantly reduces the computational burden here.
And in context of this same thing, like if you put this mixture, I mean, I understand that it can take care of the selection, but then you don't get something like a limiting Gaussian structure in this, right? I mean, it gets mixed up with everything, right? I mean,
well, I think it's more like if with this analogy with the deep learning, I think it would be what people do in practice, namely to try 20 different architectures and then pick the best one. And that is, I think, the analogy here. So we put a prior weight on many different choices, and that corresponds in the deep learning world to different architectures or different limits, actually, if we look at wide networks. And then based on that, the posterior will select and hopefully somehow the best one. But indeed, yeah, so the way it's presented normally, deep learning, is we pick one architecture and then run the deep learning and see what comes out. But in practice, it's really trial and error a lot, and then that is somehow somehow modeled with the hyperprior on these different composition graphs.
So finally, this. So is there any hope of handling in the same setup of a large number of predictors, like with this, of course, sparsity in the structure? So, like instead of a fixed number of predictors, is there any hope of making this go through with the selection mechanism?
Mm-hmm. Yeah, I think so you see the gain that you get with highly complicated composition structures is not so much anymore. Yeah, so what does it matter whether you get the rate n to the minus 1 over 11 or n to the minus 1 over 12 or so? That will not really matter for you. So I think in practice, probably one can really look at a few small composition structures, and that are really the ones which provide a larger gain, and because they can pick up the main structure in the regression function, and then somehow the larger ones probably don't matter so much anymore for like the sample sizes that we know, like millions or trillions or so. But even then, it doesn't really matter, I think, anymore. So you see it in asymptotics and so, but it's not. I think for practice, probably a few simple composition structures like these additive models, generalized additive models, a bit like what Matteo was referring to. Of course, they all have a composition structure, and so try all of them and put some prior weight on those, and then probably you will be fine. That is my idea here.
Okay, thank you so much.
Sure.
Okay, so do you have other questions or? Okay, so I think we kind of come to the end of the discussion. So thanks, Johannes and Matteo again. So a very enjoyable talk. Okay, so now the webinars will go on a summer break, but we'll be back in the autumn with some more. So keep your eyes peeled for more information about the autumn series. Have a good summer.
Cool.
Bye.
Thank you very much.
Thank you for organizing, Jim. Yeah.
Yeah. Thanks a lot. And yeah.
Okay.